Hello, calculus students, and welcome to another online lesson. Today we're beginning a new chapter on probability, and our learning intentions for today will be to define probability and represent a sample space in a variety of ways. And we will know we are successful when we can solve basic probability problems. All right, to start with, in terms of notation, what is probability? We've probably heard probability numerous times before in the past. We may have seen it. We may have covered it in an earlier math class. Probability is a number. It ranges from 0 to 1, and it can be expressed really any way. Any number from 0 to 1 can be expressed, meaning you can use decimals, you can use fractions, percentages, things like that. But as far as defining probability, usually the easiest way to do it is think fractions. So I've drawn my division bar here. And in the numerator, well, actually, let's start with the denominator. When I'm writing probability, I almost always start with my denominator. And what goes there is the total. Now, this could be the total number of outcomes of a sample space or a group of things. It could be the total frequencies that you have. It could be the total number of trials you do. But some sort of total goes in the bottom. And again, I'm just going to write for now total outcomes, all the possibilities. And in the numerator, what we do is we write our desired outcomes, the things we want. So the things that we're looking for out of all possibilities. That is what probability is, things we want out of the total. When we talk about experimental probability, this is actually observed probability. Observed meaning that you can see it. It happened. It could be data we collected in the form of a survey. And based on that data, what's the probability that the next person will do a certain event or action? But if it's actually carried out, if you actually observe that data, we call that experimental probability. And oftentimes that's given to us on tables or things like that. We'll later talk about something known as theoretical probability as well, which is not observed. Some vocabulary, some of which I've already started to mention. Uh, trials. Trials is a word reserved exclusively for experimental probability or observed probability. And it basically represents each time you carry out an experiment. For example, I could flip a coin and I could do that 20 times. And maybe 12 of those I get heads, 8 of those I get tails. And so what's the probability of getting the heads? Well, 12 were heads, so 12 out of 20. I completed 20 trials, and so again, that's the number of times the experiment or whatever you're doing is repeated. You don't need to think experiment like science. You need to think experiment like an action, which is, what it's based on from science. Outcome are the different possibilities that we've got. So going back to that coin analogy, you could get a head or you could get a tail. I could flip all day long, but those are really the only two outcomes that we're talking about. Frequency is a term that just means the amount of something. Um, the total of all your frequency always goes in the denominator, and the frequency of the thing you want or your desired outcome goes in the numerator. But again, frequency is just an amount of something. Relative frequency, well, again, a frequency is an amount of something. Like, let's say I have 20 something. And you say, oh, 20, that's not so much. But, if it's 20 absent students out of a class of 30, well, that kind of seems like a lot then. Once I compare it to something, that class of 30, it's now relative. I'm relating it. Again, if we look at that root word, relate. So we need to have something to relate to. So if you take a frequency and you express it as a fraction or a percentage of the total number of trials, like 5 out of 100. Oh, 5 out of 100, that's not so much. 50 out of 100, okay, that's a little bit better. Again, we have something to compare to, and again, that would be the total. So relative frequency is basically just another way of expressing probability. The thing we're talking about compared to the total, written as a fraction. trials, we will only use that vocabulary when we talk about experimental probability. The rest of these can be used in any kind of probability in other contexts. All right, let's look at some examples. This is a case of experimental probability. It's experimental because David actually conducted a survey. He went into the mall and he handed the survey out to people walking through a shopping mall. The results are shown in this table above. We are asked to find correct to 3 decimal places or 3 significant figures the estimated probability that the next person David meets in the shopping mall falls under the following categories. Well, when we are asked to find probabilities, we need to start with a total. That total will go in the denominator of our fraction. Let's look at this, what's called a frequency table here. We'll see those a lot in this chapter as well as our next chapter on statistics. And we have different ages. For example, 0 to 19 here. There were 19 people that David interviewed or completed the survey who fell into that age group. Now, what are their ages? Could be anything from 0 to 19, but there were 19 people in that group. And then we have 45 people who fell in this age group, and then 37 and 11 in the last group. And so the question is, how many people did David survey? Well, we need to add up all those frequencies. And we end up with 22, carry the 2, 7, 10, 11, 112 it looks like. And so I'm going to use that 112 basically as my denominator for each one of these answers. The first question says, what's the probability that the next person David meets is between 20 and 39 years of age? 20 and 39. Well, that would be this group right here. Again, how many people did we have between that age? 45. 45 out of the sampled 120. You don't need labels for probability. Any labels we have, such as the top would have been number of people, bottom would have been people as well, they would cancel out. And that'll always be the same. You'd always have the same label on the top as the bottom. So there's never a label when it comes to probability. And that's it. That's experimental probability. Your total number of trials, which was 112, and then the desired outcome was this group of 20 to 39 right here. We had 45 out of the 112. So less than 40 years of age, we can go on to for part B. Less than 40, let me clean up the board here. So our 40 occurs right here. We want less than that, which would be this group here. So we add together those frequencies, which is going to be 64, 19 plus 45, and 64 again out of the total, always out of the total, 112. And then finally, at least 20 years of age. At least is a very commonly misused word in many of my classes. At least means greater than or equal to 20, meaning the least number is 20. Everything else can be that much or more. Again, it'll be out of 112. How many are at least 20? Well, that would be starting at the people who are 20 years old all the way up. And so, what do we have? 45 plus 37 gets 12, 13, carry the 1, 93. Yes, okay. So I have 93 out of 112. Experimental probability. So we've defined probability as stated in our first learning intention, and the second learning intention was to talk about ways of representing a sample space. Well, first it might help to define what a sample space is. It's the set being the key word, of all possible outcomes of an experiment. 3 possible ways that we do that are shown here. Lists is set as a set using set notation, which is something new to many of us, where we use these little, what they're called braces, not brackets, not parentheses, but braces, and something called a two-dimensional grid or tree diagrams. The one we'll use most often is probably the tree diagram, but the other two have their purpose as well. All right. So we're going to use a list, the first of our different sample space. Again, sample space, all the possible outcomes. So now we're not actually doing experimental data, we're doing more theoretical. And so we're going to list using our list notation. So I start off with my braces. I want to toss a coin. Well, if I toss a coin, what are my possibilities? I could have a head, or I could have a tail. And those are the only possibilities. I'll close my list off. Rolling a die. Well, assuming it's a standard six-sided die, like there might be in a game of Monopoly, I've got 1, 2, 3, 4, 5, or 6 dots showing on each side. Those are my only possibilities. All right, so those are sample spaces. Those are all the different outcomes. I can roll a die all day long, but I'm only going to get 1 through 6 each time I roll it. Illustrate the possible outcomes when a coin and a die are thrown using a two-dimension grid. Well, as the title says, two-dimensional, you can only use a two-dimensional grid when you have two actions occurring or two different events that you're partaking in. Here, the two things we're doing are flipping a coin and throwing a die. Now, you might do them at the same time. You might do them separately, one at a time. But that doesn't matter. We can list their outcomes together. And so what's a grid? Well, it usually starts with axes, sort of like graph paper. And basically one side of the grid is going to represent one of your actions, and the other side is going to represent the other. Again, only works for when you have two things. Three things, this will not work. So we think about the coin. All right, so I'll write that down here in red. And then I've got the die. I'll write that over here in black. The coin has two possibilities. It can be head, which I'll abbreviate with H, or tail. Order doesn't really matter here. And then for the die, we have options 1, 2, 3, 4, 5, or 6 dots showing on each side. To actually make this into a grid now, we need to connect. So I'm going to draw some lines extending from the two outcomes of the coin, and then lines extending from each of the outcomes of the die. And you'll notice my green lines intersect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. So my sample space contains 12 different unique outcomes. What would they be? Well, you can follow these along. So for example, we have tail, for example, with a 1, and that occurs right there. We have tail again, but this time we could do it with, say, a 4, and that occurs right here. Follow each of those grids right to that spot, and there's a different spot for each one. Or you can start right at the spot. For example, if I start right here where I just made that X, follow that down, that's a 2 on the die and a head on my coin. Now, for something as simple as this, I could literally just make a list. We're showing simple examples, and they become more useful as we get to more advanced ones. But a lot of times with dice, we'll use this, this two-dimensional grid to look at all the different possibilities and the number combinations here. All right, now we're moving on to a tree diagram. And like I said, these are the most useful. You can use these for as many actions as you want. You can, have 44 different actions. It'd be one heck of a tree diagram, but we're going to start off here with just 2. The same basic option that we had before. We're going to flip a coin and roll a die. And whenever you do a tree diagram, a couple things to keep in mind. The one that students most often do not do or do incorrectly is you first need to label your actions, your verbs, the events that you're actually doing. And the two things that we're doing here are flipping the coin. Oh, let's do that in green. Flipping the coin and then rolling the die. Now, no English teachers yell at me here. I realize that those are not verbs, but I'm, rolling. I don't want to put roll and flip down. I want to actually say that, yeah, I'm doing something with the coin, and then I'm doing something with the die. And those are my different actions that I'm doing, or verbs. Now, to make our tree is going to grow sideways, more like a bush. But any plant, where do we usually come from? We start with a seed. And that's what we're going to do here. We plant a seed far to the left. Notice it's not below either of my two actions that I labeled here. It's to the left of them. And I think, okay, what could a coin be? What are the possible outcomes of a coin? And as we showed before, it could be heads or it could be tails. You're welcome to abbreviate that or write them all out. And so from our little seed, we branch off into two different outcomes, either heads or tails. You'll notice that the two outcomes I have of heads and tails, they are listed right below the coin in green. That's important. It should be labeling your work. You start with the labels and then fill the information in. Now we get to the die. Well, what could happen when I roll a die? I could get a 1, a 2, a 3, 4, 5, or 6. Well, all of those possibilities could come from getting a heads first, or a heads on the coin. So I could get heads with any of those 6 different outcomes on the die, or I could get 1, 2, 3, 4, 5, 6 tails with any of those outcomes on the die. And if I wanted to add yet another event, I could do that as well. I could, roll another die or flip another coin, and then all of these right here, they would branch apart, and the same thing would happen here, and my branches would just keep getting more and more. But if you think of the end of my, tree diagram essentially, which, is right here, and think those are like the leaves. That's where the fruit comes off the plant or the tree. And so that's the important part. And we want to know, like, how many did we have here? Well, I have 1 through 6 twice. So that means there were 12 different outcomes, just as we showed on the two-dimensional grid. And I can see those all visually. I get a lot of students as well who say, well, that's kind of juvenile. That's silly. That's not something I would need to do. Again, we're looking at very simple problems right here to illustrate what a tree diagram is. We will get to more challenging problems where there'll be numbers involved on this tree diagram, where the tree diagrams will be bigger, and we'll need these tree diagrams in order to solve the problem. So I do ask that you, attempt to follow these steps, practice these, and again, if you can do it with the easy ones, it'll be a lot easier when we get to the more challenging problems. We will skip that one and save it for next time. To sort of wrap up here, part of the reason that we talk about sample space is that we need that when we have theoretical probability. We need to know what all possible outcomes are. Theoretical probability is a measure of the chance of that event occurring in any trial of the experiment. It's not actually doing the experiment and seeing how many heads and tails you get. It's listing all the possibilities and assigning a weight or a likeliness to each of those things. We use a notation sort of like function notation. Function notation would be like f of x, where x was your input. Here we use probability notation, where we have p parentheses e. P stands for probability. We'll always use p, capital P. So this right here would be the probability of an event E. E could be changed to anything, like I could change to heads. Probability of getting heads on a coin. The probability of rolling a 7 on a 6-sided die, which would be 0. Can't happen. Things like that. So P means probability. And every time we see a P, that's a number. Probability of E is a number. And that number can be any number between 0 and 1. And so I would write that number, right here, whatever that is. Probability runs a scale. Again, we said it can be on the low end, 0. On the high end, 1. Right in the middle, we'd have 1/2 or 50% or 0.5 or something like that. And if you have a 0 for a probability, it means it will not happen, will not occur, no chance. If you have a 1 for your probability, that's a guaranteed chance. It will happen, guaranteed. If you have a 0.5 or a 1/2 or a 50% probability, that's equally likely of happening or failing. 50-50 chance, you hear that all the time, and that's 0.5 probability, equally likely. Everything in between that's less than 0.5 but greater than 0, we say that is less likely to occur. could still happen. It's not zero, but it's less likely to occur. And then everything in between 0.5 and 1, we say, is more likely to occur. And that's the idea of probability as a scale. But again, just numbers, numbers between 0 and 1. And finish with, we have complementary events. If there is an event E, then E prime, and we say that as prime. E prime is the complementary event of E. The probability of some event plus the complement, or the probability of its complement, always add up to 1. So if you want to know the probability of something not happening, all you do is you take 1, which is 100%, and you subtract the probability of that thing occurring. To give you an example, if I know that it's got a 30% chance of rain today, well, then the probability of it not raining today would be 1 minus 0.3, or 100% minus 30%. Again, you just subtract the thing that you don't want, and whatever's left is everything else. And that's complement, and those can be very useful. All right, so that was a lot of little stuff. The one example, oh, I've got one last one for us to do here today. Go through this one quickly. Mr. Peacock's 3B Calc class contains 27 students, of which 13 are boys. What is the probability that a randomly selected student is a boy? Well, we have to ask ourselves, what's the total? And in this case, I'm going to use the notation probability of a boy, or we could say probability of B for shorthand. And the probability of boy, again, is always the total, and there are 27 students, and 13 of those are boys. So the probability of a boy is 13 out of 27. Now, 13 is slightly less than half of 27. So this is a slightly less than likely chance of the next, student becoming a boy, or the randomly selected student being a boy, though it's very close to equally likely. Second part says, what is the probability that a randomly selected student is not a boy? Another way, of course, saying this is that, what's the probability they're a girl? But probability not boy, so I'd write boy, and then I'd have a prime, which means not a boy. And that is equal to the whole set minus the probability that they were a boy, which leaves me with essentially 27 over 27 here, minus 13 over 7 is 14 over 27. 14 is just slightly more than half, and so this would be a slightly more likely chance to occur. All right, so that's complements, and our notation also illustrated for you. A few problems from the book. On page 570 and 575, you can skip 1C on 575. And we will have a test on vector equations next class. And we will see you then.